Hey folks, this is Horner, and we're going to go ahead and work through A5. This one says it said that people behave really weird during a full moon. They want to know the force of the moon on you. So they gave us the distance to the moon, and they also gave us for this one the mass of the moon. And so we're going to use our equation. The force of gravity from the moon on you would be equal to big G times the mass of the moon times your mass, all over the distance between you and the moon squared. So this is 6.67 times 10 to the negative 11th times the mass of the moon, which is 7.35 times 10 to the 22nd. And we're going to multiply that times your mass, which is 50. And we will divide all this. Let's clean this up a little bit here. We'll divide all that by the distance squared, which is 3.84 times 10 to the 8th. So if you go through and do all that math, we've got to make sure we square this thing on the bottom. If you do all that math, you should end up with 1.66 times 10 to the negative third newtons. So it is very, 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 very small. They want to know, does the moon attract the student with force greater than, less than, or the same as the force with which the student attracts the moon? And we know due to Newton's third law, it would be the same. It would be exactly the same. Let's go ahead and go to the next one. Next question is A, number 6, and it says the tiny, tiny planet Mercury has a radius of 2,400 kilometers, and that'll be really important here in a second, and a mass of, and this should be, according to your packet, 3.3 times 10 to the 23rd. Kilograms. They want to know what is the gravitational acceleration. So we have to remember our equation is G is equal to big G times M over the distance you are from the center of that planet squared. Now we can go ahead and plug everything in. So this would be 6.67 times 10 to the negative 11th. The mass is 3.3 times 10 to the 23rd. And we're going to divide it by the distance squared. Now be careful, because notice this distance is in kilometers, and we really need it in meters, so it'd be 2400, and then we need to put in 3 more zeros since it's 1,000. So there are 1,000 meters in a kilometer, and then this needs to be squared because it is distance. When we solve, you should end up with 3.8 meters per second squared. They want us now to compare the motion of a ball dropped on the surface of Mercury to that of a ball dropped on Earth. Remember, on Earth, gravity is 9.8 meters per second squared, and on this planet it's only 3.8, so the ball would fall slower. So it would fall slower. And that is number 6. Let's go on to the next one that is possibly on the test. Well, I guess it is on the test. This one is the acceleration due to gravity on Venus is 0.89, that of Earth. The radius of Venus is 6 times 10 to the 6th. They want to know what is the mass of the planet Venus itself. So first thing we need to do here is let's figure out what G is on Venus. So G on Venus, I'm going to put V, is equal to 0.89 times the gravity on Earth, which is about 10. And so when you do that, you get 8.9 meters per second squared. Next thing we need to do is use our G equation. So G is equal to big G times M all over D squared. And this equation is for Venus. So this would be, all these would be for Venus itself. We know that gravity is 8.9. We know that on Venus, we know big G here is 6.67 times 10 to the negative 11th. We know the mass of Venus is what we're looking for, and we're going to divide that by the distance, which is 6.05 times 10 to the 6th, but make sure that you square it. Go ahead and solve for M. When you solve for M, you should get 4.9 times 10 to the 24th kilograms. This mass is a little bit, so this one is a little bit smaller than Earth, than the mass of the Earth. If you were to go on a diet and weigh in, you definitely want to stand on a scale on Venus because the gravity is a little bit less there and you would weigh less. So that is number 7. Next problem that we want to do is number 9. This one actually counts for one problem because there's just basically 2 parts, even though it's 2 problems on the sheet that you have. Ceres is a asteroid that we're approaching here in February 2015, so that's kind of exciting. The mass of this asteroid is 9.46 times 10 to the 20th, and the radius is about 4.25 times 10 to the 5th. They want to know what is the acceleration due to gravity on this thing. So the first thing that we need to do here is go ahead and list our equation. Remember, our equation for gravity is equal to big G times big M. And we're going to take that and divide it by the radius of the asteroid squared. So we're going to plug everything in, 6.67 times 10 to the negative 11th. Multiply that times 9.46 times 10 to the 20th. And we will divide it by its radius squared, which is 4.25 times 10 to the 5th. And we have to make sure that we square that. If we don't square it, we're in trouble. And when you do all your math here, you should end up with 0.349 meters per second squared. And that would be the acceleration due to gravity. Notice it's really, really small. The other thing they want us to do here is find the escape speed. So remember, escape speed is equal to 2 times big G times the mass of the object you're trying to get away from divided by that object's radius, or the distance from the center. So this is equal to the square root of 2 times 6.67 times 10 to the negative 11th times the mass, which is 9.46 times 10 to the 20th. That one's hard to see. And then we're going to divide all that just by the distance. Notice the distance here is not squared, and that distance is 4.25 times 10 to the 5th. And if you do all that math, you should end up with 545 meters per second. And those are the problems that you'll need to know for the test for universal gravitation. And that is the end of the PowerPoint.